Hello everyone, welcome to Virtual SAC2020. I am Fulei, and this talk is about related key and single key attacks on block cipher gift. Firstly, we give a brief overview of our work. We construct the first 25-round attack on gift 64 utilizing the related key rectangle attack model. For gift 128, the previous longest attack is the 26-round single-key differential attack proposed by Chen et al. In this work, we marginally reduce the time complexity. We also propose the longest related key attack on gift 28, that is, the 23-round related key rectangle attack. In this talk, I will mainly introduce how to perform the 25-round related key rectangle attack on gift 64. Now, let's start with the introduction of gift. Gift is a lightweight SPN block cipher proposed by Bennett et al. At CHES 2017. What is shown in the figure is a two-round gift 64. Gift utilizes a 4-bit S-box in the substitution layer, and the linear layer is a bit-level permutation. Gift has a linear key schedule. The 128-bit master key is divided into 8 16-bit key states, K7 to K0. In each round, each key state is updated by the same linear shift operation. For gift 64, the round key is K1 concatenation K0. Since the key schedule of gift is linear, once we get the master key difference, all the round key difference can be determined. Next, we introduce related key boomerang attack and related key rectangle attack. Boomerang attack is proposed by Wagner at FSE 1999. The main idea of boomerang attack is to attack long round cipher with short round trails. The target cipher is decomposed into the upper part E0 and lower part E1. Suppose that E0 has a differential trail alpha to beta over K difference delta K with probability P. E1 has a differential trail gamma to delta over K difference nabla K with probability Q. Then the probability of the boomerang distinguisher is P square Q square. To be specific, if we choose two plain tests P1 and P2 with difference alpha and delta K, and we ask for the cipher types C1 and C2, XOR C1 and C2 with difference delta, we get two new cipher types C3 and C4. We decrypt C3 and C4 with the key difference nabla K and get the plain tests P3 and P4. Then the difference of P3 and P4 will be alpha with probability P square Q square. Rectangle attack is a further development of boomerang attack. As we can see, boomerang attack is a chosen plain test and a cipher test attack, while rectangle attack is a chosen plain test attack. In the rectangle attack, we choose 4 plain tests and ask the oracle for the cipher tests. The probability that the difference between C1, C3, and C2, C4 is delta, or the difference between C1, C4, and C2, C3 is delta, equals to P square Q square multiplied 2 to the minus n, in which n is the block length of the target cipher. The dependency between the two trails over E0 and E1 should be carefully handled. Sandwich attack was proposed to deal with the dependency. Sandwich attack decomposes the cipher into three parts. The middle part handles the dependency. Here, we simply denote the propagation probability between beta and gamma over Em as PR of beta to gamma over Em, whose value is denoted as R. Then the distinguishing probability will be P squared Q squared R. Generally, Em will be a one-round or two-round switch. Next, we will explain how to calculate R. Firstly, if Em contains one round, then there will be one nonlinear layer in Em. The propagation is shown in the right figure. Note that in the right figure, we omit the linear layer operations and the symbol S represents the nonlinear layer operations. The probability over Em is actually the probability that the difference between x3 and x4 equals to beta on condition that the difference between x1 and x2 is beta, the difference between y1 and y3 is gamma, and the difference between y2 and y4 is also gamma. The boomerang connectivity table is a Xbox level table. Here, phi is an invertible function. BCT records the number of solutions that the difference can spread from beta to gamma and back to beta through the function phi. Therefore, the value of R can be calculated by the BCT of the Xbox. Secondly, if Em contains two rounds, then there will be two nonlinear layers in Em. The propagation is shown in the right figure. Here, we omit the second linear layer operations. For the first Xbox layer, we should calculate the probability of the difference propagation from beta to gamma double prime and back to beta. For the second Xbox layer, we should calculate the probability of the difference from gamma to beta double prime and back to gamma. This can be captured by the BCT. Notice that the value of beta double prime is determined by the value of beta prime. So we also need to include the cost of difference beta to beta prime through the Xbox layer. And this is what the boomerang difference table concerns. In the following, we introduce how to increase the probability of the boomerang distinguisher. In the original boomerang distinguisher, the value of beta and gamma is fixed. In other words, the attackers only pick one value of beta and gamma. Instead of requiring a specific beta and gamma, we can count all the possible beta and gamma values to increase the probability of the distinguisher. Suppose that there are U trios with fixed input difference alpha and master key difference delta INIK0 named in L0I. And there are V-trios with fixed output difference delta and master key difference delta INIK1 named in L1G. Then each combination of L0I and L1G can possibly contribute to the distinguishing probability. The probability of the new boomerang distinguisher, which is denoted as P hat squared Q hat squared, is the sum of the probabilities of each combination of L0I and L1G. For the sake of description, We give a definition of the clustering of the related key differential trios utilized in an R-round related key boomerang distinguisher. The set Ci of R0 alpha delta INI K0 and BCR0 contains all the R0 round trios with fixed input difference alpha and master key difference delta INI K0. Due to the limitation of computing, we only care about the trios with probabilities no lower than 2 to the minus BCR0. The set CO of R1 delta delta INI K1 and BCR1 contains all the R1 round trios with fixed output difference delta and master key difference delta INI K1. Also, we only care about the trios with probabilities no lower than 2 to the minus BCR1. The clustering of the related K differential trios utilized in an R-round related K boomerang distinguisher is composed by all combinations of trios from set Ci and Co. We hope to increase the probability of the related K boomerang distinguisher by searching the clustering of the trios. To search the clustering of the trios, firstly, we need to study how to search related K differential trios with high probabilities. We propose algorithm 1 based on Massey's algorithm to search related K differential trios with high probabilities. And based on algorithm 1, we propose algorithm 2 to search the clustering of the trios utilized in the related K boomerang distinguisher. In the following, we explain how to search the related K differential trios applying Massey's algorithm. Firstly, we explain the definition of weight. Suppose that L is an R-round differential trio with probability P, then the weight of L is denoted as the negative logarithm of P with base 2. The weight of round I is denoted as Wi. Massey's algorithm is a branch and bound depth first search algorithm. To search the R-round optimal weight Br, the program needs an upper bound of Br, which is denoted as Bcr. All the I-round optimal weights B1 to Br-1 are also needed. The output difference of the nonlinear in round I is denoted as .yi. The search process starts from .y1 and recursively traverses all the choices of .y1 to .yr. For each candidate of .y1, if W1 plus Br-1 is no more than Bcr, then the search process turns to traverse all the choices of .y2. We apply Massey's algorithm to search related K differential trios of gift. The search space in the related K scenario is much more bigger than in the single K scenario. So we add 3 constraints to limit the search space. Firstly, we restrict the input difference in round I to 0 and traverse I from 1 to R. Then the search process is divided into 2 parts. The forward part starts from .yi plus 1 and the backward part starts from .yi minus 1. Secondly, since the key schedule of gift is linear, we can control the round key differences by controlling the master key difference. If the round number R is no more than 10, we restrict the number of active bits in the master key difference to no more than 4, and if R is greater than 10, restrict the number of active bits to no more than 3. Thirdly, when R is greater than 10, we restrict the number of active Xboxes in each round to no more than 5. Benefiting from these three constraints, we found the optimal related key choice of gift on the limited search space for up to 15 rounds. Compared with the previous results, our results marginally update the lower bounds of the weight of the optimal related key choice. Next, we introduced how to apply algorithm 1 to search the clustering of trios utilized in the related key boomerang distinguisher. To construct a boomerang distinguisher with high probability, the first step is to determine all the choices of alpha and delta. We call algorithm 1 to search all the R0 round related key trios with minimal weight on the limited search space for E0. The minimal weight is denoted as BR0. Each trio provides a candidate for alpha and delta INIK0. The second step, for each candidate of alpha and delta INIK0, call algorithm 1 to determine the set Ci of I0 alpha, delta INIK0, and BR0 plus BW. In other words, we search all the R0 round related key trios with fixed input difference and master key difference and whose weight is no more than BR0 plus BW. Similarly, we search set CO for each candidate delta over E1. The last step is to calculate the probability of the boomerang distinguisher composed by each combination of alpha, delta, and the master key difference. It's obvious that not all combinations of beta and gamma can contribute to the distinguishing probability. Some combinations are incompatible. The incompatibility between beta and gamma is covered by the BCT or BDT. If one combination is incompatible, the value of BCT or BDT will be 0. If EM contains one round, then the probability can be determined by BCT. If EM contains two rounds, we need to firstly determine the value of beta prime, beta double prime, gamma prime, and gamma double prime. Because of the Xbox layer, we should heuristically traverse the values of beta prime and gamma prime. Next, I will introduce the details of the 25-round rectangle attack on gift 64. We construct a 20-round boomerang distinguisher. The round number of E0 is 10, the round number of E1 is 9, and the round number of EM is 1. The optimal weight of 10 round related key trios found by algorithm 1 is 20.415. The 9 round optimal weight is 13.415. We apply algorithm 2 to search the clustering of trios and calculate the distinguishing probabilities. The maximal probability of the boomerang distinguisher is 2 to the minus 58.4 457, and the corresponding value of alpha, delta, and master key difference are listed in the table. We put the 20 round distinguisher at the 4 to 23 round. Append 3 rounds at the beginning of the distinguisher and append 2 rounds at the end of the distinguisher. Then we get a 25-round key recovery model. You can read our paper for all the details of the attack. And to conclude, in this work, we concentrate on how to increase the probability of the related key boomerang distinguisher by considering the clustering effect. We apply Massey's algorithm to search related key differential trios of gift. We propose algorithm 2 to search the clustering of related key trios utilized in the related key boomerang distinguisher. Finally, we construct a 25-round related key rectangle attack on gift 64. Thank you.